In the last part of this chapter, we want to talk about specific examples of projective varieties called projective hypersurfaces. And just as for the affine case, we say that the projective variety inside Pn is a hypersurface if it is of pure dimension n-1. And in fact, this definition also works for arbitrary varieties. You have, let's say, an irreducible variety of dimension n, then a subvariety is a hypersurface if it's of pure dimension n-1. Now, in the affine case, y inside an, we have seen that the ideal of y inside an is in fact principal. It's cut out by a single equation. And then we could define the degree of y to be the degree of this equation. And the same will be possible in the projective case. So if we have such a projective hypersurface, then its projective ideal is principal, generated by some homogeneous element, and then we define the degree to be the degree of this homogeneous element. And so in the proof, we want to basically reduce to the affine case. And we first prove a special case, namely that X does not contain this VP of X0, which we see as kind of this linear space at infinity. And it doesn't contain it, and equivalently, it doesn't contain it as an irreducible component, as we're going to see. And if we have this assumption, so it doesn't have this part at infinity, then the claim is that if we intersect with an, then of course we get an affine hypersurface, and the projective closure of this is equal to all of X. And so for this claim, let's prove this equality here. So one direction is pretty easy because y is of course inside X, and so X is closed, so it's the closure of y is still contained in X. One inclusion is straightforward. For the other inclusion, we do have to use that this here is a hypersurface. And so for this other inclusion, let's say X has some irreducible decomposition into R parts. Then we claim that for all I, this ith irreducible component is not contained inside this linear space at infinity. If it was contained, then I claim we get a contradiction for dimension reasons. Because you see, I mean, X being a hypersurface is pure dimension n-1. So all of these xi have already dimension n-1. This line at infinity also has dimension n-1 because we know it's isomorphic to Pn-1. So these are two irreducible spaces of dimension n-1, and then you cannot have then if we had the containment here, xi is contained in here, then we would actually have an equality. Because otherwise, well, you have a chain of n-1 inclusions of irreducible spaces, starting from a point to xi. And then if you had one more strict inclusion, then this would have dimension n-1 plus 1, so n. And that's a contradiction. So somehow we cannot have this containment here. So in the irreducible component, irreducible decomposition, none of these things is contained in VP of X0. And so if you intersect with the complement of VP of X0, so with an, then you don't get an empty set. And what you do get is an open subset of this irreducible space xi, non-empty. And then we had a remark which said that an open, non-empty subset of an irreducible space is in fact dense. So these things are dense in the xi, and then y is of course the union of all these intersections here. And this is then dense in the union of all the xi, namely in X. So this shows that indeed we have this, this equality here. And then the fact that it is a hypersurface just follows from the fact that this here is of pure dimension n-1. And then we have seen that we have all of these parts here, that y is the union of all these parts, and these are open subsets of these irreducible spaces of dimension n-1, so they're still of dimension n-1. Okay, so that's where we are so far. We have reduced to the case of an affine hypersurface whose closure is X. And then the affine hypersurface, by the thing that we had before, this is principal. So it is cut out by a single equation F. And then we had this proposition about the projective closure in the case where you take the projective closure of something cut out by a single equation. This projective closure is actually just cut out by the homogenization. And so in this first example, at least we have proven that X is cut out by a single equation. And the general case, if we don't assume that, that we avoid this VP of X0, well, assume we are in the general case, then X still has an irreducible decomposition. Some components will not be contained in here. And then we might have one more thing, namely this component here. But then this X prime satisfies the condition of the first part. So X prime is cut out by a single equation. And then X is just cut out by the equation where you multiply this by X0. And so in the arbitrary case, we have also found that X is cut out by a single equation. What we want to show is that its ideal is generated by a single equation. But now we just want to apply the Nullstellensatz. So we are in the case X is V of F. F is homogeneous. Then let's say in this unique factorization domain, we can decompose F into its irreducible factors. And then as an exercise, if you like, to show that each of the irreducible factors is still homogeneous. And then when you take the radical, what this just does is it sets all these exponents to 1. So the radical is then just cut out, or it's just generated by the product of these irreducible factors without the exponents. And so this is principal, and then the proof is done. Okay, and then we can generalize the definitions that we had before. So if you have a hypersurface, we have now this well-defined degree, and then if you're of degree 1, then you're called a linear hypersurface, which is sometimes also called a hyperplane. If you're of degree 2, then you're a quadric hypersurface. If you're degree 3, a cubic hypersurface, and so on. And then I wanted to conclude the chapter with just some bit of an outlook of some results that we don't really have time to discuss, but which are pretty cool. So the first is the theorem of Bézout. And this says, if inside P2 projective plane, you have hypersurfaces of degree D and E. So for example, here in P2, we could have a surface of degree 2 and a surface of degree 3. Then they intersect in D times E points if you count those intersection points with the right multiplicities. So here in that example, degree 2 and 3, the expectation is that you have 2 times 3 equals 6 intersection points. And I mean, I did draw it in this case here so that you have 1, 2, 3, 4, 5, 6 intersection points. Now it might happen, like if you imagine you take this blue thing and just move it slightly here, then this point and this point will come together to an intersection point, which looks like this, of multiplicity 2. And then you have to count it with the right multiplicity. And in general, it's a bit tricky. So there's a recipe for computing these multiplicities from the defining equations. So there's just a formula, which I could write down. And then once you count all these points with multiplicity, and I guess here you also need to assume, I guess I forgot about this. So here you need to assume that these are hypersurfaces which don't share an irreducible component. Because, I mean, if you take 2 times the same hypersurface, then it intersects itself in infinitely many points. But if you exclude this case, I'll correct this. If you exclude this case, then you really have D times the intersection points. Okay, so that's one thing, and that's the kind of one of the starting points of this area of intersection theory in algebraic geometry. Another thing to be a bit cautious about. So in the proof above, with the hypersurfaces, everything worked very nicely. We reduced to the affine case, and then the projective closure was cut out by the homogenization. So this was very nice. But in general, things are not so nice. In general, it's not true that the homogenization of an ideal is generated by the homogenization of its generators. And to see a concrete example, you can take the ideal J in two variables, cut out by x1 and x2 minus x1 squared. So the individual vanishing loci of this are the red and the blue part here. And so the common vanishing locus, can just check, it's just the single intersection points, just the origin, 0, 0. Now the origin, the single point set, this is still closed in P2. We have seen points in P2 form closed sets. So taking the closure doesn't add anything. We just get the same point back. But then if we just take the formulas that we have and just homogenize the two generators, then you see here we have to multiply. So we have to bump this up to degree 2. So we have to multiply by x0 like this. And then if you look at this vanishing set, so this forces x1 to be 0. And then once x1 is 0, you just have x0 or x2 equals 0. These are both solutions, so you get 2 points. So this one is the point, this is the origin 0, 0 in projective coordinates. And this one is a point at the line at infinity. So you added an extra point in this vanishing locus. So this result, which would be nice to have, is actually false. So you can't just generate the ideal by the homogenizations of the generator. Instead, what you do have to do is you need to have a special generating set. So for this ideal, you can't just take any set of generators and homogenize them. But if you take a particularly nice set of generators, which form a so-called Gribner basis, so they must satisfy some extra conditions, then if you do that, then indeed it's true that the homogenization is generated by all these homogenizations of the generators. And in principle, there exists a computer algorithm to, given such a J with some set of generators, you can do an algorithm to find some Gribner basis, so new set of generators, and then you can from this lemma get the homogenization. So in principle, that's something that the computer can do. Okay, so that's everything about the topology of projective varieties. And next, we're going to see how do we put regular functions on those things.